As we all know, the time is 10 in the morning, and we're an hour late. Maybe I should just stop in half an hour. Anyway, I'm going to skip to the final series of topics for the class, which is reinforcement learning. We will have. I'm still keeping my schedule a little flexible because A, Thanksgiving. B, we have one guest lecture coming up, which is Graham Neubig talking about text processing. Graham Neubig is one of the biggest stars in the world at this point when it comes to you working with neural network models for modeling language. And he also happens to be, by the way, a fantastic teacher. So you get a guest lecture from him. This means that the schedule basically leaves us with 1, 2, 3, 4 lectures before we are done. And I have to cover 4 lectures in reinforcement learning and variational autoencoders. And at some point, something's going to drop. VAEs are this very special topic. That topic just happens to fall in the schedule. It's a one-off lecture. It's actually 1.5 lectures, which never gets done any semester because somehow I managed to sheave it out of the schedule. So this time I might just record the lecture if possible. Now, then another thing that's coming up which causes a bit of an issue is that I'm going to be traveling to Israel for a week. And so during that period we will have either the guest lecture or one of my Rafael covering for me. So I don't know how we'll fit this. You probably have you've probably already been notified about the poster dates. They're on 5th and 9th. We were trying to get 5th and 6th, but as it happens, everybody has their posters at the same period. So the specific location where we were trying to get our posters set up wasn't available, and while we were trying to figure out what to do, all the slots got taken up. So we're left with 5th and 9th. What we are doing is trying to make sure that everybody gets a fair deal in the sense that you're all expected to turn in your posters by the 5th, just so that you don't have one group of students getting 4 extra days, right? But the reports are going to be due over that weekend, right? Also, the Slack period for homework 4 is also in that weekend. Anyway, so today I'm going to be talking about the basics of reinforcement learning, and we'll continue this in the next class, and in the 3rd class, hopefully, I'll manage to get all the way to using deep neural networks for reinforcement learning. For the next couple of classes, we're going to go over the basics of the underlying statistical models themselves. So this is kind of a slightly tangential pair of lectures where we're not going to be talking about neural networks at all. We're going to be talking about Markov decision processes, and this plot over here is how the entire understandability of this particular sequence of slides is going to go, right? You're somewhere close to 0, and then it's all the way south. So bear with me. You have to pay attention. So here's this little story. This is a little problem that often comes up with in your job interviews. So pay attention and answer my question, all right? There's this room, and Flyda the spider is sitting at this far corner, rubbing his hands in glee, and rubbing her hands in glee. And Spy the fly is sleeping happily at this near corner. Now Flyda only always walks along the edges, and she begins walking. Whenever she's at any corner, she's going to randomly begin walking around down one of the 3 edges. It takes her 1 minute to go from one corner to the next. When she arrives at some corner, she randomly chooses one of the 3 edges that follow, and she's going to go down that edge to the next corner. Eventually, so when she gets at any corner, she's going to choose one of the 3 edges, which means she might also be turning back. And when she gets to the fly, she's going to eat the fly. So what is the life expectancy of Spy the fly? How would you solve this problem? Anyone? What? Pardon me? Yes, but if she's going to be taking 1 minute to cross an edge, and then anytime she arrives at a corner, she randomly takes one of the 3 edges with equal probability. So what is the life expectancy of the fly? Where would you begin? So here, yes. Correct. Yes, so she has a probability of 1/3 of coming here and 1/3 of coming here. So there's a 1/9 that she'll come this way. There's a 1/9 that she'll come this way. It's 2/9 that she's going to take 2 minutes. But then there are many ways of doing it in 3 ways. She could be doing one. Well, there's no way of getting there in 3 steps, right? But there are many ways of doing it in 4 steps. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Right? 1, 2, 3, 4. Many, many ways of doing it in 4 steps. So 0.9, or this is half raised to 4 times 2, right? Or half, no, it's going to be 1/3 raised to 4 times 2 times 4 times the number of different ways of doing it. It will get to be a really complicated problem, right? There's a very simple way of doing it. Let's assume that the life expectancy of the fly is T1 when she's at this corner, that it's T2 when she's at this corner. Remember, just because she's at this corner doesn't mean that the fly is dead in a minute. She could just take any of the any path, right? So T3 here, T4 here, T5 here, T6 here, T7 here, and T8 of course is 0. Once she arrives at the corner, she's going to eat the fly, right? What can I say about the relationship between these times? So if she's over here, with a probability of 1/3, she's going to take 1 minute plus T2, right? If she's over here with a probability of 1/3, she's going to take 1 minute plus T4. And probability of 1/3, it's 1 minute plus T3, correct? So I can actually write it like so. It's going to be 1/3 of 1 plus T2, T1, plus 1/3 of 1 plus T3, plus 1/3 of 1 plus T4. I can write this for each of my corners, correct? And so I'm going to get 8 equations, 8 unknowns, easy to solve, right? It's not as complicated as it looks. Make sense to everybody, right? This is the Bellman equation. It's the basis of pretty much everything we're going to be doing. And what if the room has many corners? We can expand the same idea to all of these corners, right? Switch gears a little bit. Learning to play chess. Back in 1997, the IBM built the first computer to actually beat the world champion at the time, Garry Kasparov. But before that, there was a computer which was the first to beat a grandmaster. Do you know where that was built? Yes, right here in CMU. It was a PhD thesis. It was called Deep Thought. Thomas Anantharaman, who actually wasn't even working on chess. He was originally working on processors to perform dynamic programming. And he decided to apply it to a problem. So, why not chess? And so he came up with this algorithm which used his processor, and eventually didn't even need his processor to play chess. And it turned out it was pretty darn good. So it was so good that it beat a grandmaster. Then he went to IBM, continued working on it, and developed Deep Blue, which beat Garry Kasparov. And after that, no human world champion has ever beaten a chess game. And these days, your standard iPhone is going to be able to beat the world's chess champions, right? Of course, back in 97, it was considered, chess was considered the epitome of everything that's difficult about AI, till we beat it. And now, after that, they said, okay, chess is too easy. It has only 10 raised to 120 states. Let's go to something that's slightly more complex, Go. It has 10 raised to 200 states. And so Go was the epitome of everything that was difficult about AI till, of course, 4 years ago. Our deep learning based systems beat Go. But then suppose I asked you to build a game, to write a program for playing chess. How would you go about it? Simplest thing to do, just make a table of rules, right? But if you make a table of rules, it knows how to play the game, it doesn't know how to win the game. So you could begin try saying, if you're in this position, do this. If you're in this position, do that. But how many such rules are you going to be able to write? And who's going to sit down and write the rules? Right? There are going to be millions and millions of rules. Remember that the game has 10 raised to 120 states. You're going to have to write rules for every one of those guys. Right? It's not going to be feasible. And yet, you can come up with general principles, but again, who's going to enumerate the principles? How do you know they're right? How do we do it? Right? So we do it by playing, by observing. The tree of possible moves is exponentially large, and we sort of play games, sort of watch others play games, read about games, and based on these we learn to generalize. We say that if a specific combination of a position and a move always leads to losses, you're not going to play that. If it always leads to wins, you're going to play that. If it leads to wins more often than it leads to losses, you're going to play that. If you're a smart person, not a regular player, if you're just a regular player, you're going to say this one always leads to wins, or most frequently leads to wins, and then you'll play that move. But if you're slightly smarter, you're going to say that if I play this move, in the next move, my opponent is least likely to find a winning move. And then you play that move, right? Or you can keep planning further and further out, and instead of trying to maximize your ability to win, you try to minimize your opponent's ability to win, and that's a safer way of playing the game, right? But then let's computationalize it. I want to computationalize the whole process. So I want the computer to learn how to do this. So let's start out by drawing a diagram. The circles are game states. There are an exponentially large number of these states, 10 raised to 120 for chess, as I said. And in the beginning, you don't know if any of these states are good or bad. Now, each of these states, from any state, there's only a finite number of moves you can make. So from each of these states, you can transition to only a small number of states. You can't go everywhere, right? And so the figure doesn't show the arrows. Then you play a very large number of games. And each time a board position leads to a victory, you're going to give it, say, a little green color. Each time it leads to a loss, you give it a little red. So you play a game. You won this game. Here is the sequence of moves which led to the victory. Now observe that I'm only highlighting every alternate step because every other step was played by your opponent, right? So this is the sequence of moves that actually led to a victory, but these are winning states. There's one little issue over here, that while you can be fairly certain that this guy led to a victory, you can be less sure as you go further and further out because you have fewer and more options. Yes?
Why aren't you coloring your opponent's states in red? Because it caused them to...
I'll be doing that, right? Okay. So as you go away from the beginning, as you go away into the past, you're not going to be coloring your state so brightly green. You're going to be coloring it less green. The first move, there are so many possible options, you can't even be sure that it is that move that actually caused you to win. So maybe you don't even assign it a color, right? So the color is going to fade off as you go back. But then you play a game and then you lose. You do the same strategy, and you color the red moves, the losing states red. And then you play many games, some of which you'll win, and some of which you'll lose, right? Now, when multiple games visit a state, so you might have hit a state and won in one game and lost in the other. So when you win, you're going to give it a green. When you lose, you're going to give it a little bit of red, because you're always going to be including your current experience into your knowledge of the state of the world. So as you keep playing, some states will get greener, some will get redder, some that can lead to both victory and loss will get shades of yellow. And you don't just have to learn from your moves, you can learn from your opponent's moves. Every alternate state is going to be red, right? You can learn from others' games. You don't have to be the person playing the games. And you can begin coloring the states, adding colors to the states in exactly the same manner. You can go and open up books, look at thousands and thousands of games and begin coloring the states. And to really speed up matters, you can play with yourself. Especially if you're a computer, a human being is going to take 6 hours to play a game, a computer is going to finish that game in a few minutes, right? So the computer can play tens, hundreds, thousands of games with itself every day and learn really fast. So a schizophrenic computer can actually play thousands of games with itself in the time that it takes to play with another person. And eventually you're going to get lots and lots of board positions with different shades of green, some more winning, some more losing, some indeterminate. But then it doesn't matter how many games you played, there are 10 raised to 120 states. If you spend every second from here till the end of the universe playing a game, making 1,000 moves a second, at the end of when the universe ends, you will still have 10 raised to 120 states that you haven't visited. Because the fraction of states that you would have visited is so small, it's insignificant compared to everything that is possible. So all of these guys are not going to be visited. And you're going to have to figure out how to color these guys. And that you will from the ones that you did visit. And then you color them up, right? And you learn how to do that. And once you learn it, you would color them. And then you get a new test game. You get some position. At that position, you can use different strategies. Here are the various places you can go to. I can take the move that takes me to the greenest adjacent state. Or I can make a move that maximizes the redness of the adjacent states for my opponent. Or I can go take 2 steps ahead. And I say if I play this move and the opponent plays his best move and then I play the next move and then the opponent plays his best move, at that position the opponent should have the worst chance. And I can keep going further and further out and sort of plan further. And the further out you look when you plan, the more successful you're going to be in winning the game, right? Simple strategy. And this is something that you can actually code in, even just the way I explained it to you. It's not so hard. Once you understand how the whole thing is set up, you could probably sit yourself down and write yourself a not very shabby little chess game, right? So this process, both of these are what are called Markov processes. There's something special about here. It didn't matter how Flider the spider got to a particular corner. The future only depended on which corner she currently was in and not on how she got there. So also in the chess game, it doesn't matter how you get to the current state in the game. Once you're in a current state in the game with a specific board position, the future depends only on the current board position and not how the board position was arrived at. So both of these are Markov processes where the future depends on where you are and has no relation to how you got there, right? That's the definition of a Markov process. So there's something also special about this class of games, a class of problems, like in the chess game. While you are playing, you will not know whether what you're playing is good or bad till you get to the end of the game and either win or lose. So these are playing chess, right? Or playing Go. Something like investment. I make an investment today. Was it a good thing or a bad thing? I'm not going to know for a while. I am driving traffic. So I change lanes. I speed up. I brake. I do not know whether what I'm doing is actually going to help me get home faster, sooner or faster. I change lanes. I run into a traffic jam. I brake. I cause a traffic jam, right? And so these are all things. Optimizing for getting to the goal is very hard because you don't know about the outcome of what you did until you actually get to the end of the game, right? And many others. These are all reward-based problems. The common theme is that these are control problems where your action begets rewards. You win the game, you get home faster, you make money in the investment market. but not deterministically, because when you play a chess game, your opponent also makes moves. When you drive, the rest of the people also do stuff. When you invest, the world responds to your investment, right? So the world, you're interacting with the world, and this interaction, you're getting rewards, but the manner in which you get rewards depends not only on your actions, but on how the world responds to you. And you will not know it if you've been rewarded for a very long time until after you've made the move. And in spite of all of that, eventually you've got to figure out in each situation what is the best move to make, right? So from experience of belated rewards, you must learn to act rationally, maximize your reward. Okay? So here's the general cartoon of the world. You are the agent, and the agent operates in an environment. The environment is the game, the market, the road, what have you. And you take actions. The actions affect your environment, which changes in a somewhat unpredictable way. You change lanes, you change the traffic pattern. You make a move in chess, your opponent responds and changes the state of the board as well, right? And you can't be sure how your opponent is going to respond. And that is going to affect your situation. But somewhere in between, every now and then, you get a reward, which may be instantaneous. You get instantaneous rewards. You change lanes, you get to speed up for 50 meters. So there's a little bit of a reward. It's a different thing that those 50 meters you gain now may come at the cost of delaying you by 3 hours because something else happens, or you get stuck in a lane that doesn't move. But you have an immediate reward. Or the reward may not even be apparent till the end of the game, like in the case of chess. And so the challenge is, how does the agent behave to maximize its rewards? Now, let's look at this from the perspective of the environment, the game or the investment market or the traffic. So the environment receives some actions from the agent, which is you. You change lanes, you make an investment, whatever. The environment changes in response, and then it rewards. We can see if you anthropomorphize your environment, the environment rewards you. It gives you a reward for whatever action you took. It lets you speed up by for 50 meters, or maybe you get the joy of having taken a pawn. So from the agent's perspective, here's what happens. The agent observes the environment. Obviously, you're driving, you're seeing the traffic. You're playing the game, you're seeing the board, right? You take an action in response to what you observed, and once you take an action, you get a reward. You change lanes, you speed up for 50 meters. You move your queen, you eat a pawn, right? So you observe the state of the world, you take an action, you receive a reward. So this is all the agent is going to see. It's going to see the state of the world, take actions, and receive rewards. And the agent is required to take a plan such that the cumulative rewards it gets over the entire existence of the game or whatever it is engaging in is maximized. So here's the agent's perspective of the world, and here is the environment's perspective of the world. Let's formalize the whole thing, right? At each time t, the agent makes an observation OT of the environment. The agent takes an action AT, or you can change the sequence, it doesn't really matter. The agent receives a reward, which is the outcome of what it has done earlier, and then plans its next action. So the exact sequence in which you arrange these is kind of immaterial. You can view the reward as the outcome of the current action or the past action, doesn't really matter, right? And at each time t, the environment receives the action AT that the agent took and gives the agent a reward in exchange for this action, and then changes its own state and produces the next observation, right? So let's look at this guy. What does the agent actually perceive? From the agent's perspective, this is all the agent really sees. The agent has a history. If the agent is keeping track of everything that's going on, it sees an initial state of the world, gets an initial reward, takes an initial action. Then, as a result of this action, there's a new state, a new reward, and then it takes the next action, and so on. So the agent sees a series of observations, rewards, and actions. The total history at any time is the sequence of observations, rewards, and actions. And this is what you really want to model. And you want to model this such that at any time you can take an action, condition on the history, that everything that you've observed so far, everything that you've done so far, and everything that you've received so far, such that the total reward you will get from the beginning of time to the end of time is maximized. If you're an investor, you want to make sure that the cumulative money that you get back from the market is maximized. How you actually compute your reward will depend on the specific game, right? On the other hand, if you're playing a chess game, you don't really care if you've lost your pawn and your queen and such like. You're interested in winning the game, but losing pawns and queens might also account for the fact that this helps you with, not losing pawns and queens, or winning pawns and queens helps you win games, right? Now, the environment perspective. The environment first. To explain the environment, we can define a state for the environment. The state fully captures the current status of the system. So, for example, if you're in an automobile, the state is going to be the combination of the position, the velocity, the acceleration, everything of every single car on the street. So the state defines the complete situation of the system, everything, every last bit, whether you see it or not. And so, so if you're in a traffic, you're speaking of the position, velocity, and acceleration of everything on the road. In chess, it's the state of the entire board, every single coin, every single on every single square, right? This is the state of the game environment. And the environment state is what actually decides your rewards. The current state of the investment market decides whether you're making money or not. The current state of the chessboard decides whether you're going to be able to take a coin or whether you're going to win the game. So, and it's a complex combination of many things, right? This is the environment. You can assume it to be dynamic. It keeps changing. And the agent's actions affect the way in which the environment responds. So, for example, if the agent is changing a lane, that's changing the environment. If the agent is making a move on a chessboard, it's changing the environment, and so on, right? We're going to assume that the environment is Markov. Now, here's the thing. The environment, well, what it means is that we're going to assume that the current state of the environment completely specifies future possibilities. It doesn't matter how the environment got to its current state. Just current state that it is in specifies all future determines the future possibilities. So the environment's future only depends on its present. This is an assumption that we will make, but as we'll see in a minute, this assumption is largely valid for the world, right? Why is this valid for the world? Let's go back to an old case, the story that we began with, the spider and the fly. Now, in the original case, how did we define the system? The spider was in one of 8 corners, right? And when the spider was in any particular corner, it didn't care how it arrived at the corner. Once it arrived at a corner, it could take any of the 3 edges with equal probability, right? So this guy, Flider, he has a cousin or a brother glider. She has a brother glider who's a little more discriminating. If he comes up a particular edge to a corner, he's not going to turn back. He only takes one of the other 2 edges, right? So unlike Flider, who could take any of the 3 edges, including going back with equal probability, this guy doesn't turn back. So is this spider Markov? Anyone? No? Okay. Would anybody think he's Markov? Yes. So, right. So it all had to depend on how you define the state. So if I thought of my states S1 through S8 as my corners, then if you were in S1, you could go to any of these three states without caring about how you got to S1 if you were the first spider. But in the case of the second spider, if your corner is the state, then the previous state that you arrived from actually ends up mattering. So from that perspective, it's no longer Markov, right? But then I can redefine my state. I can redefine my state as this ordered pair, which is S0, S1, which is which corner did my spider begin from, and which corner did it end at, which is the edge. And then from S0 to S1, I can go to any of the S1 star edges, right? And they're going to be only two. But then if I define my state in this manner as pairs of ordered pairs of states, now in this meta state, where it is an ordered pair of corners, the process is Markov, right? And so this one can be viewed as Markov with an appropriately defined state. But then see, there's a difference between the state as we see it, define it over here, and the state as you define it when you think of it as the corner. So the apparent state of the system is the corner that the spider is in, but I can define an information state, and an information state is the ordered pair of corners. And if I think of this process in terms of information states, now it suddenly became Markov, right? So suppose I have these two guys, Flider and Glider, have a cousin, Spider, whose behavior at any corner depends on the previous 10 corners that he has been to, right? He has a long memory. And so he sort of decides what he's going to do next depending on what he has done in the past 10 minutes. Would that process be Markov? It's still going to be Markov, right? Because now I can define my information state as an ordered set of 10 corners. So there's the notion of an information state. It doesn't matter how long the memory of the spider is. If it's finite, eventually I can define an information state that makes the process Markov. The only situation where I cannot really make the process Markov is if the memory of the spider is infinite, at which point it basically there's no way for me to come up with a clear specification of information state, right? And so if you assume a finite horizon of memory, I can always define an information state that makes the process Markov. The number of states in the system is going to grow exponentially with the memory, but that process still remains Markov. Now that means that I can actually model now in the real world, although your real world has infinite memory, it's perfectly acceptable to approximate it as saying it has finite memory. The memory may be very deep, it may be 3 months, it may be 3 years. In a chess game it may be 25 moves. It may be, if I decide that the memory of my chess game is 30 moves. Most chess games are completed in 30 moves, right? My information state is always going to be finite. In any case, in chess there are only 10 raised to 120 states, so the information state is always finite, right? But I can always, in pretty much most situations in the world, it's perfectly acceptable to assume that the true environment state is Markov, that the probability of the next state given the entire history depends only on the state at the current time and doesn't depend on how it arrived to the current state, so long as the state you're speaking of is the information state, right? Now, the agent's job is to try to maximize his or her reward in engaging with this environment. So ideally, if the agent knows exactly how the system is going to behave in any particular state in response to any particular action, what reward it will give, and how it's going to change the state. If the environment agent knows this, has complete information about the system, then given enough computation power, that too is an issue, right? Given enough computation power, the agent can sort of compute all possibilities and decide what is my best action to take at the current time, right? That's assuming the agent. If the agent doesn't know everything about the information about the environment, then what can the agent do? The agent can try to model the environment. And so the agent will, basically the agent will formulate its own model of the environment, which must ideally match the true behavior of the environment as closely as possible. But the agent must do so based only on what the agent has observed so far, because the agent's experience itself is finite, whereas the environment itself could be infinite. Again, going back to chess, if you consider every chess game that has ever been played in the history of the world and all possible states that have been visited, you have still basically not visited any of the states that the chessboard can be in. Pretty much the entire set of 10 raised to 120 states remains unvisited, right? So based on this really, really small experience of the world, the agent must model the environment and formulate a winning strategy based on this model of the environment. Now, for this, the agent must have an internal representation of the environment state, which may not match the true one at all. So it may be defined in any manner. Say, so how is the agent modeling the state? The agent's only experience that the agent has is the history, the observations of the world, the rewards it got, and the actions it took. It has the ORH, AORA, ORA, the sequence of those. That's all the agent is aware of. So if you think of the agent as a self-driving car, its history of the world is the sequence of picture snapshots it took of the traffic around it, how it turned the steering wheel, and how much it sped up or slowed down, right? That's all the agent really has, and based on this history, the agent has to model the environment. So basically, how is the agent going to model the environment? Since the only thing available to it is the history, it's going to model the environment state as some function of the history, right? And this can be defined in many different ways, right? And it's going to change your expectation of what is your best action to take. So consider this. Here's this little picture I lifted from one of David Silver's slides. Here's this mouse, and he is engaged to the world. The first time around, he saw two bulbs go off. He pressed a lever. He heard a bell. He got zapped. Then the next time around, he heard a bell. He saw a light. He pressed a lever. He pressed a lever again. He got some cheese. Now this time, he pressed a lever. He saw a bell. He pressed a lever. Saw some light. Pressed a lever. Heard a bell. What can he expect the outcome to be? Anyone want to take a guess? What is the next outcome going to be? Yes? If you had to guess.
The last three states are the same as the first one.
The last three states are the same for the first and the last example. So you expect him to get zapped.
Can't tell because the first state is different.
Right. Anybody have any other guess? Lulan?
Cheese.
Why?
The second row and the third row, they only switch the order.
Yeah, the lever has been pressed twice, right? In the second and the third. Our point is, you can't say, right? It all depends on how you define your state. So if I just say my state only depends on the last thing I did, he's going to get zapped. If my state says, I'm going to count the number of times the lever was pressed, he's going to get cheese. His expectation depends on how he defines the state. What is the true state of the world? You don't know, right? Because for that, you'd have to see everything else that happened over here and the internals of the world. So you see the distinction between the the information state of the world and the information state as perceived by the agent. The two need not be the same, right? And the agent has to model the state. Different definitions of the state result in different predictions. The true environment state is really not known, but if the mouse or the rat, I don't know if it's a rat or a mouse, could actually know what the environment state was and how the environment would respond, then it would know whether to expect cheese or to get zapped, right? So the agent goes about modeling the world. Now here's where we're going to assume that the agent, we're working from the agent's perspective all the time. Keep in mind that the environment really has its own dynamics. It really has its own behavior. The environment is this entity all by itself. But we are the agent. We're going to have to guess about the environment. We're going to have to take actions to maximize our rewards. Make sense, right? And so we're going to assume the environment state is Markov because, as we saw, that's a perfectly reasonable assumption to make in this world, right? So that means that the probability of the state at the next time depends on the current state and not how we got to the current state. Now, in theory, if the agent doesn't observe the environment's internals, the agent cannot model what he observes as Markov. So it's very simple, right? Even if the environment only has a one-step dependence, but if the agent is not able to observe the internals of the state and can only see how the state changes its behavior, or why the state changes, but only sees the outcomes, observes the world, then it's not correct for the agent to model the system as Markov because it's not Markov. A simple example of this is hidden Markov models, for those of you who are familiar with it. From the perspective of the sequence of observations, given the previous observation, it's impossible to predict the next observation. You have to see all infinite possible observations to predict the next observation, but given the state of the system at the previous time, you can predict the current observation. So the system itself, the environment itself has just a one-step dependence. From the observer's perspective, the dependence is infinitely deep. So it's trivial to prove. But we're in the business of assuming things. So, and we are going to be working off the observations. So we're just going to assume that things are Markov. Keep in mind that the world may not follow your assumptions, right? Which is where we come up with this other thing. We're going to talk about observability. I can think of saying that the agent knows the system's internals. It observes the state. At any time, the agent is fully aware of the environment state. What it doesn't know is how the environment will respond. So there are two different ways of thinking about it. The agent neither sees the environment state nor knows how this environment will respond to its actions, or the environment agent always sees the entire state of the environment. The only thing it doesn't know is how the environment will respond. So we are going to work with this assumption that the agent always sees the entire environment state, like a chessboard. When you're on the chessboard, you see the entire chessboard, right? What you cannot predict is how your opponent is going to move. So in this case, we will call this the formal mechanism that is used to define this model as called a Markov decision process. Now, more realistically, the agent won't observe all of the state. Imagine you're playing a chessboard. Even though the entire chessboard is out there, your eyes, if you're an amateur like me, focuses on one small part of the board. You miss the bigger picture, right? You have a partially observed environment state. So if you're driving in traffic, you're not going to be able to see the entire traffic. You're only seeing the things around you. So those processes, we will model them. We call them, the mathematical model for it is what we'll call a partially observable Markov decision process. In both cases, the environment's dynamics are not known. The only distinction is that in one case, you assume you can see the state. In the other, you cannot see the entire state. In both cases, you don't know how the environment is going to behave. That is what you're trying to model, right? And we're going to focus on the fully observed thing because it turns out that the partially observed version is just a special case of the fully observed version. So let's go back. Let's first talk about the Markov process itself. What is the definition of a Markov property? The state of the system has a Markov property if the future only depends on the present. Like in the case of the spider, the next step that the spider will take only depends on where it is. So that's a Markov process. Even if you have glider, who's glider's brother, who doesn't turn back, that process is still Markov, because the only thing that matters is which state he's in currently, and not how he got there, right? So that's a Markov process. Formally, you can say that the probability of the state at time t plus 1 given states at 0 to t is exactly the same as the probability of the state at time t plus 1 given st. It becomes independent of 0 through t minus 1, states at 0 times 0 through t minus 1. And as we saw, you can define your information state to have this property for any process that has a finite horizon to its memory, right? So here's the first formal definition. A Markov process is a random process where the future is only defined by the present. In other words, it's memoryless. And it's fully defined by a bunch of things. First, you need to define a set of states, because these are the complete set of states that the process can be in, number one. Then you want to define state transition probabilities, like in the case of the spider. If you're in any given state, what are the probabilities for the other states at the next time? So you have a set of state transition probabilities, P of Si given Sj, which is what is the probability that given that you're currently in state Sj, what is the probability that you will be in state Si at the next time? Formally, the Markov process is the tuple, which consists of this entire set of states and the entire set of these probabilities, transition probabilities. And so here, when I say P of S given S prime, this stands for P of St plus 1 equals S given St equals S prime. That given that you're currently in state S prime, what is the probability that the next time you're going to be in state S? And I'll just use the shorthand. P S prime as this is the source, this is the destination, right? So now, in a chessboard, the number of states is finite, 10 raised to 120. So I can actually write out all the parameters of this, of the dynamics that define the dynamics of the process in a big matrix, right? So where I have the number of states the environment can be in, the number of states it can go to, and what is the probability that if it's given in any particular state, at the next time it's going to be in the other state. So PS1 S1 is the probability that given that it's in currently in S1, it's going to go back to S1. PS1 S2 is the probability that given it's in S1, what is the probability that it's going to go to S2 at the next time. So each row is going to sum to 1, because if you're in S1, you have to go to one of these states at the next time, right? Or more generally, if you don't have a finite number of states, if your states are a continuum, like the velocity of your car, then you want to think of this transition probability as some sort of a function of the current state and the next state. And typically we will have some parametric model for this function, okay? So in this case, what would the transition probability matrix be if you're speaking of the spider who walks down one of the 3 edges with equal probability? Anyone want to take a guess? What's the transition probability matrix you're going to be? Yeah? What would the transition probability matrix be for the spider here?
Every row there will be 5 0 and 3 elements will be 1 over 3.
Every row there will be 5 zeros and 3 elements are going to be 1 over 3, right? And the 3 elements are going to be the 3 corners that the spider can go to. It's a very easy thing, right? So over here, what is the transition probability matrix going to be? How many states does the system have? Anybody? 64? Pardon me? 24? Yeah. Why 24?
So for each of the 8 states, there's 3 possible ways you could calculate states.
So because you're effectively an ordered pair of corners is a state. That's an edge. The cube has 12 edges, right? So 12 edges, each edge you can go from left to right or right to left. So there are 24 states, right? What will the transition probability matrix be like over here, yeah, for this guy? Each row will have 2 non-zero entries. The rest of them are going to be 0. So it's very simple. You know what this means. Now, so this is a very simple Markov decision process. This is a Markov process, but we are not really interested in Markov processes. Markov processes by themselves are boring because you're just talking about spiders randomly wandering around rooms without a purpose in mind. It becomes more interesting when you introduce this notion of a reward, where you have a Markov reward process, which is a Markov process where states give you rewards. At each state S, upon arriving at that state, you obtain a reward R drawn from a distribution P of R given S. So when you arrive at the state, you get a reward, and the reward, because remember the state is really the environment, right? It may be your model of the environment, but it's the environment. And what does the environment do as soon as you take an action and it puts you in a specific state? It gives you a reward, right? And so in our little analogy, spider analogy, upon arriving at any corner, there are these little swarms of flies at every corner. Upon arriving at any corner, the spider may catch a fly from this swarm hovering over there. The rewards are corner specific and probabilistic. So different corners have different size swarms with flies of different sizes, let's say. Each swarm has a different distribution of rewards, and the spider, when it arrives at any corner, is going to catch one of those flies with some probability, right? So it's not always, when it comes to any corner, it's not always going to catch the same fly or a fly of the same size. It's going to catch one fly from the distribution of flies, the swarm of flies hanging around that corner. So would this be a Markov reward process, where you have this one static fly? Anyone? Lulan, is this a Markov reward process? Explain.
You can choose multiple steps to reach the position of the fly.
Yeah, but there was a little more that we said about the Markov reward process, that every corner has a probability distribution of rewards, right? So how would this be a Markov reward process?
Only that position.
So every other state has a reward, but the reward of 0 has a probability of 1, and all other rewards have 0 probability. This one corner has a reward of 1 with a probability of 1, and all other rewards have 0 probability. So it's just a specific case, right? So formally, a Markov reward process is this tuple which comprises states, the set of states, the transition probabilities across all states, and then a reward function, which is basically the probability distribution over rewards at each state. And then there's finally this fourth term. We can alternately think of the expected reward at each state. And then finally there's this fourth term that we'll call a discount factor. What on earth is this discount factor? So to explain what the discount factor is, let's go back to this guy over here. Now think of this fellow here, right? The guy is currently over here, and I have these 2 swarms at 2 and 3. If I think of a one-step reward, which of the 2 steps, which corner should he be going to? The one with the fatter flies, right? Assuming he's always going to catch a fly. So if you're thinking of just or this guy, if you think that this distribution is very sparse, in which case this makes more sense because there you're more likely to catch a fly, right? But that's a one-step reward. Now here, over here, there's no, by the way, there's no root from 2 to 4, okay? Note the distinction between the expected reward and the sample reward. The sample reward is the actual reward that you get. It's like if the spider goes here, it catches a fly. It's going to catch one fly. That's the sample reward. The expected reward is the average size of the fly at the corner. Right? If you went to the corner many, many times and swallowed flies, the average guy is going to be some value. So the expected reward is what you may expect to get. I'm going to use the capital R. The sample reward is what you actually get, which is a small r. Okay? And so here, now let me change this picture a little bit. The spider is going to keep wandering around the room, okay, around the room, and as it approaches each corner, it's going to swallow a fly. But the spider has the option of landing, is originally hanging from some thread, from some mythical ceiling above this box, and can land at any of these corners to begin eating flies, okay? So before she begins wandering her room, which is the best corner for her to land on? Because once she lands, she's going to begin wandering around the room and eating flies. Which would be the best corner to land on? In this picture, she has a choice of 1, 2, or 3, right? Here's the point. The spider, before she lands, has no way of knowing what the room is like. Okay, so if I make this guess, you need to know the long-term consequences of landing in these corners, right? Where can she expect to get more food in the long term from? And so this means, let's say I assume that I allow the spider a practice run, or a practice run or two, where she's allowed to once land on corner 1 and then wander around for a while. Then she's allowed to land on corner 2 and wander around for a while. And then she's allowed to land on corner 3 and wander around for a while. And then you grab her away and say, now you decide the corner you must be landing on because you're going to be spending the rest of your life on this room. Okay? You've been given practice runs. Yes?
So we are restricting that the spider can only see 1, 2, and 3 states, right?
No, it says that that's where it begins from.
I mean, like it could begin at 4 also, right?
That's a restriction in this particular example. No, you could potentially begin at 4. I'm just assuming for this hypothetical example that she's allowed to land. She's landing from the top. She's not allowed to land at 1, 2, or anything other than 1, 2, or 3. But it could be 4. It doesn't really change the basic problem itself. Okay. So if I make this restriction, and if the spider is allowed to make a practice run, then what is her best way of formulating a strategy for the future? Each time she's going to land in the corner, and then she's going to wander around, correct? And then after she wanders around, she's going to make some guess about how much food she can get in the long term if she lands in that corner. She would get this for each of the 3 corners. Then you yank her off and drop her. She's going to pick the one that is best for her, right? So she must use her practice runs to assign a value to each of the corners, which is guess how much food she would get in the long term from that corner, right? And so let's say she starts at corner 3, and from 3 she does a practice, which is, okay, shown by the lines. The actual sequence of reward she's going to get, is R1 here, R2 here, and then from here she's going to go to R3, then R4, R5, R6, R7, R8, R9, R10, 11, 12. She just gets this sequence of rewards, okay? That's the practice run when she landed at corner 1. Now, is this practice run going to be always the case? What she got in this practice run always going to be the case in the future? She cannot really be sure. She knows she landed at the corner 1, so she can be fairly certain that about the reward that she got in the first corner. But even at the second time instant, there were 3 possibilities where she could have wandered. She picked one of those. And the fact that she got R2 is no way indicative of the typical reward she's going to get the next time she lands at the corner 1 and begins wandering, because she may not even go to the same corner, right? But at least you can say she has a horizon, she can look around and she can decide. But then R3, she has even less of an idea of what R3 really means, right? As she goes further and further into the future, what she experienced starting at R1 becomes less and less reliable, which means a better guess of how good it is to land at corner 3 is going to be R1 plus some discount factor R2 plus some other discount factor R3 plus some other discount factor R4. You keep trusting what you saw in the future less and less and less from the starting point, right? And you want these discount factors to be less than 1, because you don't want to be, in fact, you want them to keep shrinking as you go out further and further into the future, because you're trusting the future less and less and less, right? And mathematically a really good one is some gamma raised to I, which kind of makes sense. If you're 2 steps into the future, your uncertainty about the future is squared if you're 3 steps in the future, it's cubed. It makes sense. Intuitively, it makes sense. Also, this has the nice property that if you sum this gamma series all the way to infinity, it's actually going to be finite. So you have this discounted return assigned to to the experience, which is the return to which is the future reward all the way to the end, but each future step is slightly less believable. So basically, as she keeps wandering down, the weight she assigns to each reward that she got keeps going down exponentially, because the possibilities, regardless of whether she started at R1, R2, or R3, in the distant future they all look the same, right? So the discount factor is the belief in the predictability of the future. Now, if the future is totally unpredictable, then you don't want to even look at what happened at time step 2. So gamma is going to be 0. On the other hand, if you're sitting there and you can see exactly what the future is going to look like, then you can say the future is very clear. What I saw is very typical of what I'm going to get, and that's what I'm going to use, right? And so this is the myopic view, where you don't trust the future at all. This is the far-sighted view where you just sort of hyper-optimistic about what you experienced the first time, and that it's actually what is going to happen every single time. The reality is you've got to be somewhere in the middle, right? And so there's some peculiarity with the notation. I won't get into the peculiarity with the notation. It has to do with which time instant you assign rewards to, but the concept is clear. So let's say she started at this corner and got all of these rewards. She got a small fly of size 1, then 2.7, 1.2, and then after eating all of these flies, she died at time 10 because of indigestion, right? Now, are these sample rewards or expected rewards? They are samples, what she got on one run, okay? So what are the expected rewards at each time? There's no way you can know. You don't know the distribution. From one run, you cannot tell me what the expected reward is, right? You're only seeing sample rewards, but you're trying to predict expected rewards, okay? And then under what condition are the sample rewards and expected rewards going to be the same? No. So we're speaking of the condition, right? Yes. Yeah.
When there is no randomness.
When there is no randomness in the reward at every corner is unique, right? Then the two are going to be the same, right? The sample is what sample you got, which fly you caught. And if that sample reward is the expected reward, it means all flies in that corner are the same size. Yeah? Okay. So let's say I use a discounting factor of gamma equals 1, which means I'm really trusting the future. Then this is the sequence of rewards I got. The return is the discounted sum of the sequence of rewards. Okay? So what is the return at time t equals 1? Can you tell me?
GT would be the summation of worth and rewards.
So at time t equals 1, that's going to be 1 plus 2 plus 0.7 plus 0.2, 1.2, right? What is the return at time t equals 7?
It would be 1.2 plus 2.
1.2 plus 2 plus 1, right? All the rewards going out into the future from there. So this is the returns. The returns are everything that you got into the future from that point till the end of time, but without discounting. And are these sample returns or expected returns? You're computing them off samples, right? So these are sample returns. Now, suppose I decide to use a discounting factor of 0.5, then what is the return at time t equals 2? Can you tell me?
It would be 2 plus 0.5
2 plus 0.5 times 0.7 plus 0.25 times 1.2 plus 0.125 times 0.5 is the weighted. So, but this is the discounted return at time t equals 2, just to give you an idea of what these return values are, right? So again, discounted returns by themselves carry a fuzzy meaning. Why should we discount something that we've already observed? If we are discounting something, they make sense as samples of possible future when you're at any state, right? So what I mean, basically I'm saying that although I actually exactly observed this, if I think of this guy as my starting point, this sum is not the actual my actual expectation of what will happen every time I land at that state, because the future is diverse and gets more and more diverse as you go further into time. And so you want to discount the future more and more and more, right? So it makes sense when you think of the samples as a possible future when you're at any state. And if you're at any state, what is the expected return? This is going to be the expected value of that return, right? And so let's assign some values to it. Let's say the value of a state. Now the spider could land at one of three states, right? And it wandered and got an experienced, ran some experience, wandered through the room, swallowing flies for a while, and computed a discounted return at each time. What is she doing when she uses those numbers for her second visit to the room? She's using each of those numbers as a typical representative of what will happen if she starts from each of those corners, right? So she's thinking of those. What she really wants is what is the expected return from each of the corners. You want the expected return when the process begins at that state. So if I start at state S at time 0, what is my expected return? But this doesn't really depend on time, because we said the process is Markov, right? It only depends on the fact that you're starting from there. So in other words, this expected value of G0 given as 0 equals S is the same as the expected value of GT given as T equals S. I can write this as Vs, which is the expected return starting from state time T, right? And now here, let's go back here. Let's say the spider gains a reward of value 1 if she consumes the fly, and the spider has infinite patience. She can keep wandering, right? What is the value of starting at any corner? What is the value of starting at this corner? Matt? What would it be? Pardon me? So here, assuming she has infinite patience, so there is no discounting. It doesn't matter where she starts from, eventually she is going to catch a fly, right? So the value of every single state is 1. But then, so regardless of which corner the spider starts at, she will eventually randomly catch the fly, and so the expected return from any corner is 1. So the value of being at any corner is 1 for all states. She can expect to get the fly from anywhere, right? But now let's say the spider is hungry, and she's running out of reserves, and if she wanders around an edge for a minute, she suffers a cost of -1. So now there's a negative reward for getting to corners without food, right? What is the value of starting at each of these corners? Which corner will be the best corner to start from? Assuming it's not 8, right? But even, of course, she doesn't know beforehand, right? It's a one-time experience. So how would you actually do this? In this case, there's a total reward associated with each corner. -1 if the corner has no fly. Well, definitely, because it means you definitely spend at least 1 more minute exploring. And 1 if you're at the corner that has the fly, right? So the reward is going to be -1 for C1 through C7. And this is the reward, not the return, right? The reward of arriving at any corner is going to be -1 for C1 through C7. It's going to be 1 for C8. You can also assign costs for edges and things like that. I'm simplifying the problem, okay? How can I decide what is the value of each state? Now here's what it is. The value of being in state C1, I know that it's going to be, regardless of which edge I take, none of the 3 subsequent edges have any food. So there's a cost of -1 plus 1/3 the value of C2, 1/3 the value of C4, and 1/3 the value of C3. Does this look familiar? Right, this is exactly where we started off with. Except now we are speaking in terms of values. So also, you can compute this for each of the 8 guys. And so now you have 8 unknowns. You have 8 equations. You can solve for them, and you can determine the value of being at any state, right? Assuming you know the rewards from each corner, right? Or the expected rewards from each corner. So now if there are flies at every corner, the expected reward of arriving at any corner is R of Cx, which is the average size of the fly in that corner minus the penalty, right, of getting there. Now again, if you think of the spider as sort of having run through a bunch of practice runs and computing the expected reward or the expected return for every corner, she's going to, in each practice run, she's actually going to be discounting the future out, right? And so, which means that you give more importance to immediate rewards than to future rewards. If I land in this corner, I get a fat juicy fly, but then I've got to keep wandering, right? So if I do this, the same problem, the formulation for deciding what the value for each state is, stays pretty much the same. The expected value of being in state 1 is the expected immediate reward of arriving in state 1 plus gamma times the expected reward of the future states, right? Which is 1/3 of the reward or the expected return of future states. Sorry, this is going to be, so the value of C1 is the expected reward of C1, is the current reward plus the value of the future states. Make sense, right? So this is going to be R of C1 plus gamma times, which is the discount factor. You don't trust the future. 1/3 of the value here plus 1. So 1/3 of the return here, which is the value, 1/3 of the value here plus 1/3 of the value here. This makes sense to everybody, right? And what happens if gamma equals 1? This just gave you the original. What would happen over here if gamma equals 1? In this case, you're going to have a finite, just get the usual solution, right? Anyway, so the value of being in any state is going to be the reward at the current state plus the values of the future states. Expected gamma times the expected values of the future states. Okay. So the value function of a state is the expected discounted return when the process begins in that state, which is, here's the return that we saw, which is the current return plus gamma times the next return and so on. But if you begin at a particular state, so this is the return, the expected value of this guy when you begin at that state is the value for a state, and the Bellman expectation equation says that the value for any state is going to be the reward, expected reward for the state plus gamma times the expected values of the states at the next step. This is just following the same logic that we saw in the very beginning of the class, right? And as it turns out, in processes with infinite horizon, which can go on forever, the total undiscounted return will be infinite for every path. So why do you need discount factors? If I'm always going to be getting a return, then I just keep gaining and gaining and gaining, right? So it turns out that this gamma actually has an arithmetic reason to exist. That for finite horizon factors, a discount factor of gamma is good. If the game is going to end, if the spider is going to stop wandering after some time, then a discount factor of 1 is good. But if the process is infinite and you don't discount, then you're going to find that the return from any state is going to be infinite, and there's no game to play, right? They're all equally good. So there's a mathematical reasoning also for having this discounting, which is to say you want to make sure that everything stays finite. Now I can write the whole thing down as a simple algebraic equation. Suppose I have a finite number of states. I can say this is the vector of the values for all the states. This equals the rewards for all the states plus gamma times the expected value of the subsequent state. The expected value of the subsequent state for the first state is simply going to be the weighted combinations of the subsequent states, where the weights are the values of these states multiplied by the transition probabilities to those states, right? So in other words, I can write the whole thing down as the transition probability matrix times the value vector. And then once I write it like so, if I know everything about the system, if somebody gives me the entire Markov random process, then I can trivially enough say the value equals reward vector, expected reward vector, plus gamma times PV, or V equals, moving this to this side, V equals I minus gamma pi P inverse times R, right? Very easy. And when you want to plan, where do you begin? Where must you go? What is the best move to make, right? You want to always go towards the state that has the highest value, which means that you need to know the values for the states. And the values for the states are easily enough computed using this formula. What is the challenge here? Why would this be difficult? In a chess game, there are 10 raised to 120 states. The transition matrix is going to have 10 raised to 240 entries. You're not going to be inverting that matrix anytime soon, right? Secondly, if gamma is 1, it's trivial to prove that this is not invertible. So, which means that if you don't have a discount factor, You can't even invert it. So much of what we deal with is to how to tackle this problem. Anyway, let's stop right here. We've spoken of Markov reward processes, and the assumption we made is that we have this spider who's randomly wandering through the halls and grabbing flies. But in reality, the flies don't respond to the spider, right? That's the assumption that we made. In reality, the fly will respond. If the fly is standing at some corner and it sees the spider coming towards it, it's going to try to escape. If it sees the spider going away from it, it doesn't care, right? The environment, which is the distribution of the flies, depends on the action that the spider takes. And that's something that we haven't actually considered. We have neither considered the fact that the spider is not a random machine, that the spider is just not randomly wandering through the walls, it's not wandering around the room, but taking decisions about where to go. So the spider has agency, and the environment responds to the actions of the spider, right? Both of these have not been considered. So next class we'll pick up with that. Thank you.